So an intro to haloalkanes. When haloalkanes are attached to alkanes, the side group attachments are called fluoro, chloro, bromo and iodo. Here's an example of a haloalkane, 1,2,3 tribromo propane. You can see the 3 bromine atoms are on 3 different carbons, hence the name. Next we've got 1,2-dichloro 2,3-dibromo propane, and you can see that here, 1,2-dichloro 2,3-dibromo propane. The bromines and chlorines do not have to be in these positions. That chlorine could be here or there and it'd still be one position. Remember, the alternative to this is actually 1,2-dibromo 2,3-trichloropropane, where you can see that this is one position, two position, and then three position. Now we'll look at some of the physical properties of the haloalkanes. The first one is that the haloalkanes are insoluble in water. Although they have this polar haloalkane bond CX bond, it's not polar enough to make the haloalkane soluble in water. So other molecules like ethanol, methanol, they are soluble in water because they have the polar OH bond, but the CX bond is not polar enough. The main intermolecular force between the haloalkanes are permanent dipole, and van der Waals. Boiling point trend of the halogenoethanes. So chloroethane, bromoethane, iodoethane. The boiling point trend is that the iodoethane has a greater boiling point than bromoethane, which has a greater boiling point than chloroethane. This is because the iodoethane has the greatest molar mass, which leads to the greatest van der Waals intermolecular forces. Remember, these three molecules are simple molecules. This leads to the greatest number of electrons, hence the stronger van der Waals intermolecular forces. Also to consider that when you have an increase in the chain length of the haloalkanes, then you will have greater van der Waals intermolecular forces, just like you learnt about with the alkanes. So an example, chloropropane has a greater boiling point than chloroethane due to the extra carbon and hydrogen atoms, leading to stronger van der Waals intermolecular forces. The last item to consider is the bond strength of the halo to carbon bond, and you can see the trend is summarized here. So when you go up the group, Ci up to Cf, the bond strength increases significantly. So Cf is much stronger than Ci. This small diagram here will help you to envisage why that is. So the C to the F is very close to the bonding pair of electrons. The I's nucleus is significantly further away to the bonding pair of electrons. So the attraction between the nucleus of the iodine and the shared pair of electrons is weakest in the Ci. Now this then leads to a very fast nucleophilic substitution reaction when the hydroxide reacts with the Ci very quickly and breaks the Ci bond most effectively with the hydroxide nucleophile. This is summarized in these equations here. So this reaction will happen very quickly, this reaction will happen more slowly, and you can check for how quickly these halide ions are being formed using silver nitrate and nitric acid to test for the halide ions. So remember that the AgI is a yellow precipitate, and the yellow precipitate will appear fastest, and the silver and chloride ion reaction would occur more slowly, and so the white precipitate of AgCl would appear more slowly as well. This reaction here just could be carried out in a test tube with the haloalkane reacting with the sodium hydroxide. Then the nitric acid could neutralize the hydroxide, and then the addition of silver nitrate would form the precipitate. I've summarized the reaction I just described. So here are the reactants. So 2 test tubes, chloromethane, iodomethane in the 2 different test tubes. We may well need a longer chain length for this reaction, and then the reaction takes place and you can monitor the formation of the precipitate as I described.